Assalamu alaikum wa rahmatullah wa barakatuh. Our video for today is about lenses, which is from chapter 24 in our textbook. And again, let me remind you with the name of our textbook, which is Physics by Ken. So in general, in this video, we are going to talk about two types of lenses, uh, which they are convex and concave, or we can call them converge and diverge. In the next slides, we are going to see why we call the convex converge and the concave diverge. In general, our lens is a material or transparent material like glass, plastic, and you need to know the following. The index of refraction of this material has to be greater than the index of refraction of the air. So in general, as you can see here, I have a convex lens of two faces. In other words, I have two spheres, and my lens here is or has a two face, where these two faces are parts or two parts from the sphere, the two spheres, I mean. So in general, we have what's called lens mark equation, which is 1 over the focal length equal n, or the index of refraction, minus 1 times 1 over the radius of the front radius of curvature minus 1 over the back radius of curvature. Now, the trick here, how to determine the signs of the radius of curvature, and how to know which one is the front, which one is the back. So let me take the following. Assuming my object, as you can see here in this position, and I'm looking, or the viewer, in this position. So as you can see here, all the time, this face, we can call it the front face. Therefore, the radius of curvature is the red face, and the blue surface is the back face. Now, for the signs of R1 and R2, or R front and R back, should be the following. If I have convex lens, that means my radius, or the radius of curvature, should be positive or greater than 0. If it's concave, it should be less than 0 or negative. If it's flat, as you can see here, it should be infinity. Again, when I'm saying front and back, I'm taking my reference for this, which is the object. So let's go to the following example. Determine or calculate the focal length of this lens. So this is my object. So clearly, this surface is the front, and this surface is the back. Therefore, as you can see here, the front surface, or the front part, should be greater than 0, so which is positive, and the back radius of curvature should be negative. Therefore, 1 over focal length will be n minus 1, which is 1.5 minus 1, multiplied by 1 over, so the front here is 20, so 1 over 20 minus 1 over minus 20. Do your calculations, you will end up with focal length positive 20 centimeter. This will give us, or will tell us, the focal length of convex lens is positive, which means we have a real focal point. I will talk about this in more details in the next slides. Second example, I have two surfaces, as you can see here, and this is my object. So every time, determine the front and back of your lens. So this is my front, which has R1, and this is the back of the lens, which has R2. As you can see here, the front and the back of this lens, both of them should be positive because both of them are convex. So plug my numbers again in the formula here, R1 and R2, as I mentioned before, because they are convex surfaces, we have to take them positive. Therefore, the focal point or focal length equals 80 centimeter. Another example, I have this lens, which is concave, and you need to know for the concave lens, the focal point or the focal distance is negative, but let us check if it's negative or not. Now, this is my object. Determine your front and your back, or the front surface and the back surface. So clearly the front surface here is concave, so it should be 1 over minus 20, and the back surface here is convex, so it should be 1 over 20. Do your calculations, you will end up with focal length equals to minus 20 centimeter, and this showing us that the focal distance of the concave lens should be negative, which means the focal point is not a real point, it's an imaginary or virtual point. Now, another way to discuss or to see or to check the whether the focal point for convex and concave either positive or negative, real or virtual. Let us take this lens, which is convex lens, and at the beginning you need to know the following. You have to have two axes. The first axis, which is the horizontal axis, and it should be passing through the center, and the second axis, which is the vertical axis, and again it should pass through the center. It's something like I have X and Y axis. Now let us take a couple of rays where these or those rays parallel to the central axis or to the horizontal or main axis. As we know, we have a lens and we have our light coming from index of refraction to strikes the material of the lens, and we know we have two different index of refraction. Therefore, we will have, or the light here will experience a refraction. So parallel light striking with the lens, giving us or experience the what's called refraction. And the refraction ray here should pass through the to a point, certain point. Take another ray, parallel ray, and refraction passing through the same point, third ray, fourth ray, and so on. By the end, you will see all of these refractive rays passing through a certain point. So we can call this point or collect all the refractive rays, and we can call it the focal point. As we can see here, it's a real point. Now, let us take the concave lens. Same procedure. I have two axes, the main axis and the vertical axis. Let us take horizontal light or ray. This ray will experience a refraction, and you see the refraction of this ray, which is divergent. And here, take another ray. You can see the refraction or the refraction ray or refractive ray. So take extensions for this ray and this ray to collect them at certain point. Therefore, here my point is a virtual point, not real point, same as the convex lens. That's why in convex lens, we call it converging lens, and here we call it diverging lens. Now, how we can, or how can we use the convex lens and concave lens to form an image? In general, let me take a convex lens. This is my lens, and this is the main axis. This lens has a real focal point. Let me take my object, as you can see here, at a distance d sub o or d naught. I mean by d naught is the object distance, and see how to get the image. At the beginning, we have to take a parallel light, as you can see here. This light should be parallel to the main axis, and the refractive ray or light should pass through the focal point. Take another light, as you can see here, passing through the focal point, and look to the refractive ray where it's crossing with this ray. So at this point, we can say this is where, or this is where the image can be found. So from here, we can see the following. My image is real, inverted because it's below the main axis, and I think, yeah, and reduced. Note that the distance from where is the object to the lens called d naught, and the distance where is the image and the lens is di or d sub I. Therefore, we can use the lens maker equation, as you can see here. 1 over focal length equals 1 over d naught plus 1 over di. And again, I'm talking about convex lens. Therefore, the default signs for these parameters, since I'm talking about convex lens, the focal length should be positive. The distance, because it's in the front, should be positive, and the image distance, because it's in the back, should be negative. And the magnification, or we can use this to calculate or to determine if the image is reduced or enlarged or same height. We are going to use the magnification formula, which is minus d, or the object, the image distance divided by the object distance, or the height, the image height divided by the object height. And by the way, 1 over focal length is called the power of the lens. So we have a lot of physical expressions. 1 over f, it's not only it's not only for the to calculate the vocal distance. We use it again. We use it to calculate the power of the length, the power of the lens. Let me use the same procedure in order to see where is the object can be found. This is my object, and the distance from the lens to where the object is d o or d yeah, d sub o, or this object distance, taking the ray, as you can see here, parallel to the main axis, and the refractive ray, something like this. Take another ray, as you can see here, passing through the center of the lens, and now take an extension of this refractive ray. You will see it crossing with this ray. Therefore, the object, the image performed at this point, where the distance from where is the image to the lens is called d sub I, and again we can determine the properties or the characteristic of the image formed using by the concave lens as reduced, virtual, and upright, because it's at the top or above the main axis. With same procedure, 1 over vocal length equals 1 over object distance plus 1 over image distance, where is the 1 over vocal point or vocal length, sorry, is the power of the lens, no matter if it's concave or convex, and the magnification, as you can see here. Okay, let me take the following example. An object that is 7 centimeter is placed 20 centimeter in front of a concave lens whose vocal length is 15 centimeter. Determine the characteristics of the image. Okay, let us take this example, or take it as pieces. Now, at the beginning, the height of the object is 7 centimeter. The distance of the object from the lens is 20 centimeter, whereas the vocal point or length here is 15 centimeter. In other words, we can say if the distance or if the vocal length is 15 centimeter and the object is placed 5 centimeter from the vocal point. 5 centimeter here is not the object distance. 5 centimeter here is the distance from the vocal point to the object. But we are saying the distance of the object should be the distance from the lens to where is the object. Now, 1 over vocal length equal 1 over image distance plus 1 over object distance, and we are going to calculate the image distance. Do your calculations. You will get d, or image distance, is 60 centimeter. Now, up to this point, we can guess the characteristic of the object, where it should be real, because we are talking about convex lens, and inverted, because again it's convex lens, and either reduced or reduced, enlarged, or same height. To get or to make sure if it's reduced or not, we have to use the magnification formula. So which is minus di divided by d naught. It's equal -3. Now, -3 here, it's something like -1 times 3. minus 1 tell us it's inverted, times 3 tell us the image is greater than, or the image height is greater than the object height, which means it's enlarged. Now, let us check the height of the image. We calculated the magnification, and we know the magnifications equal h, or the image height divided by the object height. We know the object height. We calculated the magnifications. Now, all what we need, the image height. Do your calculations, which is m times h naught. You will get minus 21 centimeter. Again, this plus the image height is greater than the object height. Another example, an object whose height is 4 centimeters is placed 50 centimeters from the concave or diverging lens. If the focal length of the lens is 30 centimeters, determine the characteristic of the image. Using the same procedure, but be careful. We are talking about concave lens. Therefore, the focal length should be negative. Now, plug your numbers here. You will get D, or the image distance is minus 18.75 centimeter. At this point, I need to know what the minus means. The minus sign here means the object, sorry, the image location is the same as the object location. That's why the minus sign showed here. Now, to see the magnification, same as the previous example, from here, you can tell the following. Since we are talking about concave or diverging lens, the characteristics of the image should be at number 1 should be virtual. Number 2, from my virtual, upright, and from my calculations here, as you can see, the height of the image is less than the height of the object. Therefore, it should be reduced. Okay, this example, I will leave it for all of you as practice. Insert a lens of a focal length of 35 millimeter. Here, we are talking about positive focal length, which means I'm talking about a converge or convex lens. Again, we're saying here real image, which means we are talking about convex lens of a picture of has a magnification of 40. How far from the lens should be the picture located? This one too, I will leave it for all of you as practice. An object that is 4 centimeters tall or height is placed 7 centimeters from a converging lens that has a focal length of 2 centimeters. Calculate the height of the image formed by this lens. Sorry, here, this is not DI, this is HI. I'm sorry, it's type of error. This one should be HI instead of DI. Thank you, and see you in the next chapter.